So it's my pleasure to introduce Anna Erschler, who will be giving the last talk of either groups and dynamics seminar.
Thank you. Thank you for this opportunity to speak. So I will speak about a priori three topics which a priori might seem quite different, but turns out to be quite related. So I'll speak about groups. So we'll have, say, three. Group. And we want to study the following problem. The first one is an Isoperimetric problem. The second one is about dimension. For us, it would be mostly about asymptotic dimension, but several other notions would be of dimension are also relevant. Asymptotic dimension. And we will speak also about Universal Traveling Salesman Problem and invariants that could be defined in something related to Universal Traveling Salesman Problem. Just I give some definitions. So for the first problem, so we just consider the Kelly graph of our group, right? The graph. That is, we consider the graph. The vertices of these graphs are elements of our group tree, and we have an edge between G and GS if S is inside some finite generating set of G. This is the metric space we are interested in. By the way, some of our invariants and some of our questions could be studied, and several questions are asked could be asked for metric spaces, but for groups, there is a special structure that we are interested in. So this is the first problem. I give some definition. So given such group equipped with a finite generating set, we call Følner function Gs of n is the minimal cardinality of finite set V such that the size of its boundary divided the size of the set is smaller than 1 divided by n. This function is defined whenever the group is amenable, so this is one of the possible definitions of amenability. Maybe if you know that the boundary is smaller, could be chosen much smaller than the set, and we are interested in this function. But today, we will be even much more interested in the following function. It's the minimum of the diameter of such sets of diameter of V. Again, with the same condition on the set, such that the boundary is n times smaller than the set. Just a few words what we know about such functions. So maybe an easy example, easy and not so easy example. Take, for example, abelian group ZD. In this or in other groups, when I say the boundary, if you want to solve the problem exactly, then it matters what definition of the boundary we take. So in all this context, for precise definitions, there is at least 3 studied definitions. So we have a set. For me, I will usually say the boundary is the internal vertex boundary. So we have a set and we look on the points of the set at distance 1 from the complement. This is internal vertex boundary, but also one can study external vertex boundary, that is the points at distance 1 in the complement, or one can study edge boundary, just the number of edges between a set and a complement. I tried to search the literature, and my understanding that even on the D, exact solutions are not known actually. So, and even approximate solutions. So, for example, for the edge boundary, it seems it's as late as Barber and Edge 2018 for the edge boundary, where they say that natural optimal sets are good for any genetic set, but only they so good asymptotically, and it seems to be an open question if they're exactly optimal. For vertex boundaries, for outer vertex boundary, I understand some reference Wang and Wang in the 70s, Rusha for general generating sets in 95, and then my understanding maybe for internal boundary, it's not known even for ZD. But for us, it's not very important. We are interested in asymptotic of this of a function, right? And then clearly it's not important which definition they take. The boundary will change only after multiplicative constant. And for all these functions, we want to know the asymptotics. And just another maybe remark that, okay, for the D, at least it's not so difficult to see spheres are smaller than the balls. So spheres, balls, that is, are Følner sets. If you take a more general example, G is of polynomial growth. Then it's not absolutely obvious that the balls are Følner, but this is true. So balls are Følner, that is, the spheres are much smaller, balls are Følner. The oldest reference I know is Colding Minicozzi in 98. There was similar statement, maybe related arguments in a little bit different language might appear earlier, 98. And I Følner, but interesting, even in this very straightforward case, because the groups are virtually nilpotent, right? So we know very good their structure. It's an open question. Seems to be an open question. What is the size of the spheres? So we can consider the size of let's say Vn plus 1 minus Vn. Here Vn is the growth function, that is the volumes of the balls in the graph. The number of the spheres. It seems a very natural conjecture. It should be approximately Nd minus 1. This is known to be the case for two-step important groups. It's Brieussel and Ledona, a little bit more than 10 years ago. And they asked this question, actually they asked a stronger question, which recently seems turned to be out recently. There are other questions. There could be count examples, but for this question, we don't know count example. I think we shouldn't expect any, but surprisingly, we don't know even such elementary definition. Returning to our function, what does it mean? If you want to understand, are all balls optimal at least asymptotically? So, because the balls, the size of the balls is n to the d, then to say that sphere the size nd minus 1 means optimal because it's constant, they are optimal to being n Følner with boundary n times smaller. And this is not known even in this case. But what is easy to see, simply use it. Polynomial growth, right? If you look on the balls, let's look on the balls of radius between n divided by 2 and n. Like n divided by 2 and divided by plus 1, and so on until to n.
So, sorry, what does it mean to be Følner?
Følner, thank you. Følner, let's say the sets, the sequence of Følner sets, let's say omega I sequence of Følner sets. If the boundary, the size of the boundary divided by the size of the sets goes to 0, right? This is just to say Følner, and one can ask, one is interested in sequences like this, or one can ask a stronger condition for given n. We want to, like 1 over n Følner, if the ratio is smaller than 1 over n. So what I want to explain now, it's very easy to see from polynomial growth. If you look on the balls, we don't know if all of them are constant times n Følner, like in this question about the size of the spheres, but at least very easy to see. Look on the balls of radius between n over 2 until n. At least one of them should be a constant times n Følner. At least one of them should have a sphere of size smaller than constant n d minus 1. So in other words, for the Følner function, it's clear that if we identify function, which we always do up to equivalence relation, it doesn't matter if you multiply by a constant or if you multiply by argument by the constant. So Følner of n is equivalent to n to the d, where d is the growth. Right? Now, there are many open questions formulated in this very basic, using these very basic notions. So, for example, again, with a very easy argument, if the growth of the group is sub-exponential, the balls, there is a subsequence of balls, which is Følner. Now, in polynomial growth, as I said, it's known, maybe not with an optimal parameter, but the sequence of all balls, at least it is Følner. For groups of exponential growth, it's not known. Take a group of exponential growth, do all balls from a sequence of Følner sets. We don't know. In particular, we don't know even for any plain example, like for Grigorchi groups, we don't know at all. What is the size of the spheres? Should we expect maybe for all sub-exponential Følner? Also, on the opposite scale, it's straightforward from the definition. If we have a group of exponential growth, it's not possible that all balls are Følner. But it's an open question. Can we have a subsequence of balls which is Følner? Maybe never, but we don't know how to prove it. So, so this is about just comparison with the growth function, yeah?
Maybe, okay. Is it possible that the size of Vn is just a polynomial or altering between polynomials, or?
No, as I said, like a possible argument, for example, like doubling not only for groups of polynomial growth, actually for reasonable metric spaces with doubling. For example, the argument explained in Kozak-Manikotze, the spheres, the size of the spheres divided by the size of the balls goes to 0. So you mean is it possible on subsequence? No. So, and yes, I didn't explain, but it is polynomial, but we don't know the optimal degree. So maybe I don't have the time to say exactly, like holding Manikotze and a better estimate in Brieussel Vidona estimates give an upper bound for the size of the spheres. The lower bound in all polynomial growth is the same as you expect, the same as it's happened for the d. The lower bound is n to the power d minus 1, but it is known the upper bound for the spheres is n d minus some constant. So conjecturally, this constant is 1. But this is known only for two-step polynomial groups. Now, a very bad beta is in the argument of called Minikotze. Much better beta is in Brieussel donor, and we don't know what it is. But since it's really d minus something, so you see the size is polynomial. The question is only if it's exactly d minus 1. I don't know if it answers your question. And so this is about the balls. And now, maybe I draw some pictures of what happens on Z2, for example. On Z2, with at least with one definition of the boundary, the optimal sets would be balls in the Word metric that looks like this in the case of Z2, right? In the other definition of the boundary, it would be squares. Right, so this is sort of L1, this is L infinity ball, and but we are interested only up to a constant. Up to a constant, they are all the same as the balls of the metric you like to choose. And just some comment. And what about dimension? Because we want to discuss dimension. Do we see some dimension of our space from the Følner sets? Not really. Okay, in abelian case, we do see, right? In abelian case, whatever reasonable definition of dimension you will take, we'll discuss in a moment a particular one. So dimension is equal to 0, right? And so, okay, in the Følner says function n is n to the d. So you can say, oh, we see the dimension, but this is a rare case when we see the dimension, because even if the growth is polynomial, the growth is not a dimension. Take a growth like this. Dimension is free, but the growth is n to the 4. And actually, this n to the 4 is much more relevant for Følner functions. So just in general, along our Costa inequality, the Følner function asymptotically is always larger than growth function constant. And so for polynomial growth, it's really the case that is the equivalent actually, but for other groups, it could be much larger, but it couldn't be smaller. So, but for polynomial growth, it should be really, with this easy argument, we know it's the same as its growth. And for many groups, polynomial growth constant, the growth degree is not our dimension. But let me say what about diameters? Because for us today, we are interested mainly in the diameters of Følner sets. Well, the diameter of the Følner sets for polynomial growth would be linear. You can't make smaller than linear just by this inequality. But yes, but even this is a straightforward argument I explained already. It wouldn't be greater than constant times linear. That is for us linear. And so we don't. Now, if you look on the asymptotic of Følner sets, or if you look at the asymptotic of the metric function, we don't see the diameter yet. We don't see the dimension yet. Let me say which definition of dimension we want to use today. So we'll speak about asymptotic dimension. The notion of asymptotic dimension is something sort of inspired, I would say, by the notion of Lebesgue covering dimension. Just I remind, we don't need Lebesgue covering dimension, but I remind just Lebesgue covering dimension first. So if you have some space The main covering dimension for reasonable metric spaces would be the same as topological dimension. There are many ways to define it, but covering dimension defined in the following way. We have some covering. Example, I try to draw a covering of a plane. This was not very happy one. Maybe better take something with hexagons. Let's consider the covering of our space by open sets, for example. And the covering dimension divides like this. We take some covering. If we want to claim that all this, we can take a refinement. Refinement means we just take replace all the sets by possibly smaller sets. And then we see what is the maximum of the number such that the point belongs to several sets. For example, on this picture, for these points, it belongs to 3 possible sets, right? 1, 2, 3. And the dimension, the topological dimension is 3, and I will define in a moment asymptotic dimension. It will be also 3, for example, in this picture. And so what about the asymptotic dimension? It's like this. We want to consider covering of our metric space in general X. And we want that for any number R, the following holds. There exist, well, so, yes, in the wrong way. So for all F, R, there exists a covering with the following properties. So that any ball of radius R, belongs to one of the sets in the covering, belongs to one of the sets. And on the other hand, we want to have some bound on the size of our sets. And let's say diameter of such sets is at most some function of R. For the plane, for example, it's clear that such pictures provide you, yes, and we look on the numbers, we look on the numbers, look on possible D, such that each point belongs to at most D plus 1 points, belongs to at most D plus 1 points. And we say the dimension is not greater than D. For example, on the plane, it's easy to see. Just take this picture, rescale it, multiply by a constant. We see we see here the size. So each ball of radius, some constants times the size of these hexagons is it belongs to one of the sets. On the other hand, the size of our sets is just constants times this R. So such functions f of R are called control functions for asymptotic dimension. Function of asymptotic dimension, and if f of R is smaller than constants times R, if f of R can be chosen in this way, then the space is said to have Aswad-Nagata dimension. Aswad-Nagata dimension is finite. So, what is relation to our story? So, yes, control functions So for the moment, we are comparing two functions, at least asymptotic function here, which was defined here, and the control function for asymptotic dimension. Control function for asymptotic dimension was known for some families of metric space and some families of groups. Now, the asymptotic of the asymptotic function, apart from straightforward examples, didn't seem to be known in any class of groups until now. And so one of my goals to explain you how to find in some situation the diameters of Følner sets. And in the same situation, these diameters of Følner sets, so this function, ISODM, in many families of groups, turns out to be equivalent to the control function. This is our first observation. Yeah, I forgot to say, everything I guess I will be speaking on today is a joint work with invariant problem. And there is a third function related to universal traveling salesman, but since the time is limited, maybe I will try first to formulate the results about control function as a asymptotic function, and hopefully at the end at least quickly explain what is the other function related to universal traveling salesman and why it also in many families turned out to be equivalent to the control function of asymptotic dimension and to the asymptotic ones. So maybe I write somewhere here. Also, so V is our growth function. From Coulomb's law of cost inequality, what is clear about the diameters? It's clear that diameters as a term couldn't be smaller than inverse function, the Følner function, right? For us, for example, if the growth exponential, growth is exponential, no, it's not smaller, it's greater, growth is exponential, then so its diameters are greater than log Følner function of n. If this holds, one says that our group G has lossless asymptotic function. This is terminology introduced by Peter Nowak more than 20 years ago, a little bit, Peter Nowak. And he asked the question, is there at least one group which is not lossless?
Sorry, I missed the definition of lossless.
Lossless if if we have equivalence, if equivalent, so it's always greater than this expression. But if the equivalent, let's say that the group is lossless, or maybe we can say Følner function, so it's meaning Følner function is lossless with respect to asymptotic function. Why he called it?
It's for group of exponential rules.
No, it's for any group. So for any groups, you take just inverse function of the growth function. But our main interest would be exponential growth actually, and the inverse function of the exponential isoperimetric, right? And so Peter Nowak asked, do we have groups which are not lossless? there are many families of groups which are actually lossless. Why he calls it lossless? Meaning, so isodemetric function can be shown to be a quasi-isometric invariant, so it's a natural invariant, right, of our group. But do we get any new information from isodemetric function if you know the Følner function? And a slightly different question, but for regular function equivalent, right? Do we get any information about Følner if you know isodemetric, or if you know any information about the diameters, and vice versa, right? So, and lossless if we don't lose the information, if one asymptotic gives us the other. And so now I want to explain the standing. But surprisingly, actually, there are many groups which are not lossless, but somehow it seems they were not, no, this was not on until now. I say something what is lossless and what is not lossless, and what explain what is the connection to the function for the asymptotic dimension. Dimension. As several famous examples, so here would be groups. Then here I will write what are diameters, the metric function. Then control function for asymptotic dimension, function for asymptotic dimension, and I will have time quickly explain another. The first function would be elongation, something we call it elongation of slits metric. So what happens? So here we have just n to the d. Yes, the Riff product is a finite group. I write the lamp group on the right, so ZD acts on the direct sum of Z to Z, for example, which is indexed by ZD. Here, as a diametric function would be n to the d, and maybe I write also, and it would be lossless. And well, control function would be actually it's not completely obvious but true and well known. Now that a control function would be n to the d is the result of Brodsky, Didak, and Lang 25 years ago or something. So we did Lang. And this is something new, but I didn't explain because also n to the d. Or you can look, yes, or you can group on groups with finite asymptotic dimension. We assume that asymptotic dimension is finite. So if it's finite, just by definition, control function is linear. But something that Nowak has shown more than 20 years ago, the diameters are linear. Some new function here will be also linear. And then there are many other classes which are lossless. Maybe I don't list them, all of them, but at least one of them. There are some groups of Brieussel and Zheng, which given a function f, supposing that f of n divided by n doesn't decrease, so I write increase, but in fact it doesn't decrease. So these are groups that Brieussel and Zheng have constructed several years ago to explain that Følner function, if you have a reasonable function, you can, for any function, you can construct a group with a given Følner function. And so they did not describe the diameters, but this can be easily done if you know all their estimates. So their group would be also lossless. And they have really prescribed diameters. So diameters would be just f of f for any function f, such as f1 doesn't decrease, and control function. So they describe Følner function. We can describe diameters which are really very closely related to their results, but something that wasn't known that we can prove now. We can also evaluate control function of the asymptotic dimension. It will be also f of x. So like this. And then there are other families of solvable groups, like Holtz groups, which are important by a billion. So there are many other families where we also have the same answer for control function and for the geometric one. But what are not lossless examples? So the easiest example we have, take just Reeve products with an infinite group Z. Here, the Følner sets, at least straightforward Følner sets, has the sides n to the power n to the d. So more or less close to x n to the d. But for diameter, for diameters, we just our new result, the diameters would be n to the power d plus 1. And we calculated the, it's not V, so I said V, it's also Brodsky, Didak, and Lang. No, here it's very easy, it's maybe easy but known. The main thing with Brodsky, Didak, Lang, Brodsky, Didak, and Lang, that is this one for Reeve products with Z, and our function will be also like this. And so this is not lossless. I say Brodsky did actually their estimate was a little bit worse like that, but their main motivation was to understand finite asymptotic dimension or not. There still was enough, but if you look carefully on the argument, it actually give this. So for subgroups we study control function was more or less known, and our main goal is to control the diameters and to see we obtain the same answer. And for some other classes of groups, our evaluation is new even for the control function. Maybe I mention some other examples. Like one can consider something that space like shuffler group. I will define in a moment. Shuffler group on the D. In this family of groups, both control function evaluation and diameter of the function evaluation is new, seems to be new. And we evaluated, and it's n of d plus 1 also. But the Følner function is approximately x n to the d. So these examples are also not lossless. There is some interest to look on these examples, I'll try to explain in a moment, because in such equation, there is a special meaning when dimension is finite. So finite or infinite, yes, for ZD with Z, with all reasonable notion of dimension is infinite. The group contains Z to infinity, yes?
So in this table, have you taken logarithms of everything?
No, it's no, but I didn't say what is the Følner function. For the Følner function, you need to take the logarithm, you get n to the d.
Okay, go ahead.
Maybe I didn't say it correctly, but I was never writing actually the Følner function. But here, well, the emmettus is very essential. You don't take the logarithm for control function. You don't need to take the logarithm. And so, just the Shuffler group, I will say in a moment, these are groups of finite asymptotic dimension. And what is nice to know, they are also not lossless. And we have some other families, maybe I don't list them here. So for various families of amenable groups, in particular for many families of solvable groups, these groups are not solvable, but at least amenable. So we calculated three functions, the third one I didn't explain yet, and we got the same asymptotics. Seems to be a new phenomenon, I think, and even we hesitated at the very beginning, or should we expect for all groups? But we have a work in progress. Maybe I don't want to explain the construction yet, but for this comparison, control function is isodiametric. In many classes, it turns to be the same, but we know now to construct groups where they're not equivalent. So, and I'm really curious to know what is the condition to ensure the equivalent. We have different arguments. We don't have exactly the same argument in various classes, but for sometimes different reasons, we get the same function. I'm curious to know why. So, and maybe I say a few words. What is a Shuffler group? So, if you have some base group, for example, Z for us here, you consider the group of finitary permutations of ZD. Just permutation that permute only a finite number of points, and you consider extensions. You consider semi-directed product of this group by ZD. This is something it's called Lamb-Shuffler group, and so as I said, we evaluated control functions is n to d plus 1, and the emmettus is n to d plus 1. But maybe it's time for me to also define some other. The third function I want to explain. What is the first function? If we take a metric space X, what is Universal Traveling Salesman Problem? It's like this. You want to approximate a traveling salesman problem. Traveling salesman problem, you probably know, right? You take a finite set, say V in X, and you want to find the shortest path to visit all points of V. And universal traveling problem is some universal algorithm, universal in the following way. You want to enumerate all points of your space X, that is considered an order, total order on X, enumerate X. And then whatever set is given, you just visit the points with respect to this defined in advance order. Clear, this algorithm will almost never give exactly shortest path. Well, if the space is aligned, obviously it will give a shortest path, right? If you have some number of points, the best thing is just to move them from left to right. It would be the shortest path. In general, it wouldn't give a shortest path. You never can expect it. But universal traveling problem says, what is the multiplicative error? We are happy if the ratio is not too bad of this path given by the algorithm by the actual shortest path, something in computer science called competitive ratio. So we want to say, what are spaces where the competitive ratio would be nice. Something very easy to see. If you have a metric tree like this, what is a good way to enumerate the points to have a good approximation for traveling salesman? Just I have drawn the tree on a plane, and then just let's visit the points in such order. We just go around the tree, and the order is the first visit of the vertex on this picture. It's clear the path would not be greater than constant, which is 2 in this case, times the actual path. So for tree, it's very easy to see. So it's the ratio is constant. That is the best possible thing one can expect is a constant. For trees is a constant. We can show for delta hyperbolic spaces, particular groups, it would be constant. And so one of the questions can ask, what are the spaces where it's constant? It's I don't know exactly, because sometimes spaces very close to hyperbolic, but not delta hyperbolic, can have this constant. But this is, well, a typical, I would say, situation. So for us, trees and hyperbolic spaces are the best. And what happens for other spaces? The story of Universal Traveling Salesman Problem has started with a paper of Brieussel and Platzman in the 80s. I can see 82. What reduces, who studied this Universal Traveling Salesman Problem on the plane? It's the same for us to say, is it R2 or Z2? It's really equivalent problems. They studied both discrete and non-discrete contexts. And they observed there is some nice algorithm, which of course not so good as for the trees, but with some very much controllable error. So take, for example, Z2 for that. Yes, story starts with Z2. And Brieussel and Platzman introduced an order on Z2 so that the ratio, if you have k points, if your V, cardinality of V is k, the set is k, the error in this ratio, shortest path given by algorithm or actual shortest path, would be at most logarithmic. And maybe I'll explain quickly. Interesting enough that even for Z2, the question about actual ratio seems to be still open. So in the very first paper, but first I explain the algorithm, and maybe I have a few minutes to comment what is known and what is not known, how it works. The tree is not so interesting, but how you would enumerate Z2? What total order you know on Z2? I give you Z2 and ask to enumerate the points. Maybe you have some favorite orders. So I guess everybody knows lexicographic order, right? But it would be extremely bad for us. So, for example, one way to enumerate the points, just you first visit all points on one vertical line, then on the next one, and then on the next one, right? But observe that for Universal Traveling Salesman Problem, this order does not make sense at all, because take some large constant, let's say take 2k points, and here let's take the distance k, like this. This way. Yes, like this. Take k points with some projection on vertical line and other k points with projection 0. If we try to follow the lexicographic order, you will have a lot of zigzags. You will jump like this and like this, right? So while the actual distance is linear in k, right? You just visit this, but here and visit other points. If your lexicographic order will give you something like k squared. And this is not what we like. But Bartholdi-Platzman observed there is a much better way to enumerate the points. And the idea we need to take as a space filling curve on R2, on the corresponding curve on Z2. And here the ratio would be logarithmic. It wouldn't be linear. It would be logarithmic. So it's a bit difficult to draw. I'm not good in drawing the pictures, but I'll try to. You need to take something like a Menger curve. So you can construct it by substitution. If you have 4 points, you just visit them in some order. Then you take 4 tuples of 4 points, you just visit them like this. You go here. That is, if you consider them as a points, you want to follow this order, cyclic order simply, and then, but we have many more points, so we visit like this, like this, like this, and like this. This is our order on this final approximation of our Z2. Then, but we want to continue to construct the corresponding curve. We want to consider 4 things like this again. It's not very beautiful, but I mean, the curves are beautiful, but not in my pictures. So you need to consider 4 and 4 and 4. Again, 4 like this, and just on this tuple of 4, you want again just a circle thing, and here you just connect them like this, visit all this, then visit all this, and you pass the limit. This is the order of Bartholdi-Platzman. In the very first paper, they said, oh, there is the logarithmic bound, but we think it's our algorithm is very efficient. We think there is a constant ratio. This was very thick and really much too optimistic. It's not at all constant, this ratio. Until recently, the lower bound, so Bartholdi-Platzman for the ratio gives it smaller than logarithm, constant logarithm of the number of points. Until recently, the lower bound is was log something, I don't have the exact answer, but something like log to the power 1/6. And here we have Cosmas Kravaris, who is a graduate student in Princeton, who very recently improved this known for many years lower bound. And your estimate is square root of log, right?
It's over log.
Yes, but I don't go into details about log because the actual answer can be logarithm, right? And we still don't know. So the up about the logarithm seems to be a very natural question asked in some papers. So many works until now were mostly by computer science people, and so some question asked, is it logarithmic? So the Cosmos. For the plane proved something like greater, like log, okay, and with log, I don't like log, and this is surprisingly we still don't know even log, but which was very nice to know. But this is one thing. But some comment: what do we for which spaces we know there is such more or less nice saying for us logarithmic is nice. We can't explain it much better unless the group is really very close to a tree that is hyperbolic or something very close to hyperbolic. So the best answer, even for the plane, is something like logarithm. And so, but for which spaces we know that Bartholdi-Platzman estimate gives us logarithmic multiplicative error. So if we have space with doubling, so if X is a space with a doubling condition, then it's a work of G and his collaborators into something like 2005. You have the same upper bound as for Euclidean space. Our result with the one, let's say in 2023 or something, if the space, more generally, if X is of finite Asymptotic dimension, again, we have the same upper bound, which is log K. And we conjecture that it's if and only if. And we prove this conjecture with additional properties in the infinite dimension case in many families of groups. For example, for all these groups, we prove it. So now I define our actual function. So something relatively good like this logarithmic error is true for a finite Asymptotic dimension. It's conjecturally never true otherwise. But right now, I'm interested actually in groups where Asymptotic dimension is infinite. That is, asymptotic dimension is finite, but asymptotic dimension could be infinite. And I want to compare what happens for control functions, what happens for the diameters of the Følner sets in case the group is amenable. And now I want to find the function that we study here. So just take an order, right? So we have a space X. For us, mainly we're interested in group G. We want to enumerate the points and we consider some order. What do we call elongation of snake? So let's consider something similar to the picture I have drawn here for the plane. Let us consider some points, some two groups of points. We can consider finite set. We call it its snake if we consider the following things. So we consider that the diameters of one set in the other set is bounded by something, by the diameter of the snake. The diameter of the snake is maximum of the two diameters. Max diameter V1, diameter V2. And we want to study how much longer the length, that is the diameter of the set, is than the width. And so something that was very relevant even for space with finite Asymptotic dimension in connection with Universal Traveling Problem. Now, the dimension for us could be infinite, as in all these examples. And so for us, we don't really discuss the algorithm of Bartholdi-Platzman, but we look on this other invariant. We are simply interested as it is in this invariant. How much a snake can be long, how much the length could be longer than the width. So given an order, we consider the maximum of possible length given the diameter, and then we take minimum of the maximum. We take the minimum over all orders. I speak about this because about the graph, so I say minimum, I say maximum. We can define the same things in continuous set, and it's rather infimum and supremum, right? And this is our function of snakes. And so now in many situations, we calculated it, and it turned out to be the same as the control function. And now, as I said, among these two functions, we have a counterexample, though they seem to be rare. Diameters in principle could not be the same as control function for asymptotic dimension. Now, comparing to other function, a well-known control function, or this newly invented sort of by us function of logarithmic snakes, we don't know how to prove it, and the question can be asked in general, even for metric spaces. Are they always equivalent? Here we don't have current examples. We have current with diameters, but not for this other question. So I have maybe 5 minutes, 3 minutes. How many minutes? Maybe
3 minutes.
3 minutes, yes. So, okay, just a few very quick words. What else we can ask about diameters and all these functions? So far, I discussed this various geometric invariants, how they're related, right? But a very ambitious question where very little is known. And what if we know some information about this function and we want to understand something algebraically about our group? So there is one case which I wrote here, this result of Nowak 20 years ago or so. It was the first very interesting link why diameters of Følner sets are related to dimension at all. So he proved inequality between these two functions actually, and that allowed even sometimes to check if the group has infinite or asymptotic dimensions. He used the estimates on Følner sets and the corresponding statement about diameters to say that some groups, for example, some reef products are not do not have infinite dimension. Now, so for us, we have now this variety of various class. If you give me the Følner function, well, I don't say exactly the condition, but more or less, if you give me a reasonable function, which is quicker than exponential, then you would be able to construct a group which is not which is not lossless here. So no chance in general, even for a large variety of Følner function, to say the group is lossless, but there is one special case. If the Følner function is exponential, here it's an open question. Is this condition equivalent to the fact to say that asymptotic dimension is finite? And there are open question. There are many sort of competing smallness conditions for minimal groups that might, after all be equivalent. So here, Nowak he proves already that if dimension is finite, his group is lossless. One can ask the same, very similar question, but here we don't know. If the Følner function grows exponentially, is the group lossless? And something, just the very last result I want to mention. So what we prove, that if dimension is finite, the group does have what is called Shalom's property H of D. I don't have time to explain what is this property, but the corollaries are very easy to state. Take a minimal group of finite dimension. Then this group, for example, cannot be a pure torsion group, or it cannot be simple group. And here, it's very essential that the group is amenable. And for the question about simplicity, if you take Burke and Moses simple groups, they have finite dimension, but they could be simple. Now about torsion, I think it's an open question for non-amenable groups, but for amenable groups, we prove now it's not possible. So it seems to be one. So, but the very last question, we proved these algebraic consequences before. We did not know much how dimension could be used to claim something algebraic. Now we know at least something, but then one can ask, are such groups of finite amenable groups, let's say this finite asymptotic dimension, are they all, for example, elementary amenable? If the answer is yes, it would be a very, very far-reaching of polynomial growth theorem of Gromov, and which is very, very ambitious, of course, to get any generalization, but one doesn't know counterexamples. So far, we have this tiny step, first step, maybe in this very, very long road to say the group is elementary amenable. At least we can conclude that we have some portions because of Shalom's property. And I guess I need to stop here.
Are there any questions? I guess I'll have one question. So do we know that elongation of snakes can have any sort of growth?
Yes, well, up to some regularity condition, we can compute elongation of snake for the groups of Brieussel and Zheng. So we have computed it. And as I didn't write it, like for any reasonable function of n, we have a elongation f of n. Thank you for this question. Yes, it is so.
Any other questions? Well, let's thank Anna again.